QCD, I'm going to describe, first of all, as a fairly standard finite difference stencil PDE in 4 dimensions. So there's a 9-point stencil backbone probability plus a site local term. For the purposes of this audience, you can think of it as simply being the square root of the D'Alembert, which is a 4-dimensional generalization of the del squared operator. In the presence of the electromagnetic vector potential, this couples electrons to electromagnetism, producing the quantum field theory QED. And the theory we're interested in, this is a mildly nonlinear theory, so it generates a Coulomb potential, all of physics, chemistry, engineering, material science, you name it. But in the case of QCD, it generates a wickedly nonlinear theory that is confines quarks inside the proton, called quantum chromodynamics, which is only amenable, therefore, because it's so strongly nonlinear, to numerical simulation. We are performing the Feynman path integral, which is a Markov chain Monte Carlo process, through importance sampling to evaluate our correlation functions. And each step of this Markov chain Monte Carlo involves the calculation of a force, which is the gradient of a cost function, where that gradient involves the inversion of this PDE on a given particular state of the system. Now, because there are no boundaries at the length scale of the proton, there are no walls, there are no boundaries, there are certainly no aerofoils and things like that, with the result that there's a translational invariance that means that we typically are looking at regular 4D Cartesian grids with a very regular structure, right? So there's no need to have unstructured mesh, for example. Now, the advantage of that regular structure is then that a regular Cartesian data parallelism in the style of connection machine Fortran or something like that is sufficient to describe the theory, which means that we can write data parallel interfaces that then target all forms of underlying parallelism underneath this high-level data parallel interface, which is what I'm going to describe. Okay, so, come on. Since we're at Argonne, I'll just remind people that Edinburgh and Columbia worked with IBM Research designing the level 1 prefetch engine that's a part of the Blue Gene Q ASIC. So that was, if I have this right, specifically, this region here of each PU was the level 1 prefetch engine. And then as a form of co-design, the machine was in balance for QCD and many other problems, which enabled us to scale very nicely out to 7.2 petaflops and 1.6 million cores on the union of Sequoia and Vulkan before they were broken up. Okay, so with that allusion to co-design, I'm going to revisit this Berkeley roofline hypothesis, which I really strongly support, but argue that it should be generalized to being a multidimensional description where we're interested in balancing the cache bandwidths, the memory bandwidths, and the network bandwidths in a system rather than simply looking at the arithmetic intensity in terms of the floating point to memory bandwidth ratio. You really have to look at it as a rather more complex and rich system where there are different buses to cache, each level of the cache, buses to network, buses to memory, and have the intensity categorized on a case-by-case basis. And then you suffer the death by 1,000 cuts, because if any one of these is limiting your performance, that will become the rate determining step. So the target of co-design really could be to have a good programmer will saturate one of these bounds, and in a well-designed balanced machine for your particular problem, you will simultaneously saturate all of the bounds and have no particular performance limiter to your code, or no single performance limiter to your code. Okay, so with that said, we can go through, this is something that's really targeted for more the QCD audience, but we can go through and categorize how much data we access from cache, how much of it comes from memory. We process an L to the 4th subvolume on each node. Surface to volume ratio on that node, so when we apply a nearest neighbor stencil operator, we know that if you have L points in each direction and you apply a single hop finite difference operator, 1 over L of those points have to come from off the node. So that will tell you clearly the ratio between at least the cache bandwidth if this stencil operator is living in cache because of the reuse. If you have a 9-point stencil, each data element fetched will contribute to 9 of its neighbors. So you know that the ratio between the cacheable bandwidth and the network bandwidth is then 1 over L on a L to the 4th footprint per node, for example. So 1 over L of our data references come from off node. And then depending on the reuse factor that we actually get in the cache, because caches do have a finite capacity and not an infinite capacity, that this factor may be lower than the number of points in the stencil. So we have this reuse factor, which is between 1 and then stencil, depending on the details of the architecture. We can infer the ratio of the network bandwidth to the memory bandwidth based on parameters of the system. Okay, so hold that in your mind. I'm going to revisit it later when I look at multi-node performance. For single-node performance, I think there are many problems with single-node performance, threading, vectorization, etc. I think vectorization is typically the hardest problem to solve, especially hard to solve in a platform, cross-platform performance portable way. So this is a strategy we are taking. We're abstracting vectors or vectorization in little C++ classes that represent a vector of a varying and architecture-dependent length. So we have either an M256, a 128, a 512, ARM instructions or whatever that are embedded in a little wrapping class that provide arithmetic operators and transcendentals, divides, whatever, and provide an architecture-independent interface to vectorization by wrapping it and encapsulating it in a class. And then we build the rest of the application based on these vector classes. And then the vector length is returned by this class, which lets us parameterize layout transformations in a way that transforms as you transform from architecture to architecture. So we then have a bunch of vector real, vector double, vector complex, etc., vector of integer, which we then base the application on. And then when we port to a different architecture, we only require to implement something like 400 lines of code that comply to this interface, which gives us a nice way to port and to port performance between architectures. And of course, we use a fancy, sophisticated C++ template metaprogram wrapper around this. Why are we doing this, or how are we using vectors, or what's the best way to use vectors? So we are typically in QTD interested in applying small matrices, maybe 3 by 3 complex times small vectors, but having many of these because these are the coefficient matrices of our PDE. So the bad way to do this would be to try and vectorize within these rows of these matrices, because then when you come to the end, firstly, 3 doesn't divide the vector length typically, because 3 is obviously a nasty non-power of 2 number. And finally, when you come to the end of a row, even if you were to collect this matrix times vector product, you would have to collapse horizontally across the vector, and this would be a nasty latency-dependent, serially-dependent process that would not itself not vectorize well. So the trick then is to say that we're going to be doing many of these and to interleave many matrices times many vectors at the same time, each of which can then be programmed as if it was a simple scalar loop doing a matrix vector product, but the datum becomes 512 or 128 or 256 or 1024 bits long, which allows us to vectorize by going in a different direction in a way that leaves, in principle, no limit to the amount of vectorization we can obtain. And the way this is programmed then is to write a naive matrix vector product or matrix vector accumulate, but then pass in the vector type as a template parameter to this function, which lets us write it either for scalar or for 512-bit or for 256-bit, and vary by passing it in as a parameter with an explicit compile time passed in template integer for the matrix rank, which then generates well, I can't say this is beautiful code, but it's very, very flop-dense sequences that runs efficiently on the hardware. So this is the assembly that's generated. So all this C++ wrapping of the vectorization types and these functions that wrap inline intrinsics get inlined and removed by the compiler and leave you with pure floating point coming out at the end in the assembly code that's generated. So this is very like this kind of sequence that was shown for libx SMM, for example. So this runs up to 65% of peak when it's running from L2, so we're getting good performance out of this. The other thing is that Xeon cores are absolutely awesome. This code would not naively run efficiently, but the chip itself is unrolling 4 iterations of this loop in order to saturate the pipeline because it's looking so incredibly far ahead and it's out of order. Okay, so then we know how to do lots of matrix vector multiplies in parallel. generating good code from the compiler. The question is how to generate this massive numbers of parallel operations to do together. And to do this, we can look back to the 1980s, where in Connection Machine Fortran, there was this idea of virtual nodes that allowed to target arbitrary levels of SIMD parallelism on these machines. And the idea was to divider arrays, mapper arrays across virtual nodes in a user-controllable fashion, right, where virtual nodes would execute in SIMD parallel and then write high-level data parallel constructs on top of this. So those of you who remember the Connection Machine, or indeed HPF, will know that the trick was to, as we divide across physical MPI nodes in a regular Cartesian mesh, so this would represent the work in one node, you can over-decompose the subdivision to extra virtual nodes that are even smaller than the physical node, and then you write code that executes in, say, the blue region, but by magic of the compiler, or by magic of our C++ library, you have the same node execute in all 4 quadrants at the same time, doing the same thing to every element, which you know you can do because you have a high-level data parallel interface that said, do this to every element of your array in parallel, and therefore it knows what it does to one cell in the blue, it also has to do to one cell in the purple and the green and the red, right? So this is the way that we generate the parallelism in the code, by constraint, by having a high-level data parallel interface. And the point is then that for stencils, the neighbor of the blue guy is the same offset relative as the neighbor of an element in the purple as the green and the red. So all the relative addressing within one cell also applies to the other cells. So that when we access a neighbor, we can access a whole cache line size of elements of the blue. We can access a whole cache line size which is built up out of consecutive elements of the red, the green, the blue, and the purple, right? So we get 100% utilization of each cache line that we fetch, because we've padded up to that on each element of the vector. Okay, so we compose this array, this transformation where we've interleaved different virtual nodes in our array of structs of arrays inside our code, and we hide it from the user by packing everything into a lattice object, one of these lattice container classes. The way we parameterize in a legal C++ way this layout transformation to an array of structs of arrays is we pass in a vector as a template parameter to a class, which should be either scalar, vector, or matrix, and every datum within that array is of type the template parameter, which can grow or shrink according to the architecture we're compiling for. So this is the way that we pass into C++ structs, that we're going to expand out every datum to exactly the vector width of the vector unit, and then stop. And then having done this, we've hidden this horror of layout complexity inside a template, a container class, and then we operate on the containers by just saying things like C equals A star B, which are fairly simple high-level constructs, which then say for every element of this Cartesian array, A, B, and C, apply A equals B star C, and this will run with 65% of peak, and then we have C shifts and stuff like that for doing the low performance finite difference terms, which this all then, under the hood, translates to target SIMD threads and MPI efficiently within the code underneath the library. Not only that, but these types are composable, so I can pass into vector itself a vector, right? So we can make an arbitrary tensor product of indices, because we have spin indices in field theory, we have got color indices, you name it, Lorentz indices, because electromagnetic fields has polarizations, etc. And these are composable, so we can build up actually a mathematical type system which can be nested arbitrarily deep. Then we use fancy C++11 to infer rules such as scalar times scalar is scalar, matrix times vector is vector, etc. And this is applied recursively so that we can generalize to any level of tensor nest of indices and infer the matrix vector scalar rules recursively down level by level until we hit the inner scalars at the end. Okay, so as an example, this reduced something like 50,000 lines of machine-generated code from a prior package called QDP++ that Balint Yo talked about to only a few thousand lines of code enabled by clever use of C++11. We then wrap it in an expression template engine, which does all the usual loop fusion transformations and so on for complex expressions. I'm not going to talk about that in great detail, but it's a well-known programming technique. And again, we use C++11, so we were able to reduce the expression template engine for the vectors down to only about 200 lines of code. This was, again, something like 10 to the 5 lines of code in prior packages, enabled by C++11, because with C++98, you had to enumerate all the possible return types, whereas we can infer recursively the return type in all our expressions by using this auto and decal type in a nice recursive way. Okay, I'm going to skip over C-shift. This is just to convince you that policy classes are a great design pattern, but that's fairly standard. And now I'm going to focus on the stencil operator. So the idea is that we have a stencil object that's designed to assist the creation of Cartesian stencils shifting only up and down X, Y, Z, T, or if you've got 5 dimensions, W, or whatever ranks. So the code does support 1, 2, 3, 4, 5, 6 n-dimensional arrays underneath it. And the idea is that you create a stencil object where you list the directions in which it's going to shift and the displacements with which it's going to shift by, and then build up a stencil who knows only about the geometry of the stencil, and then the stencil can handle the halo exchange and communication for that particular stencil pattern, and then the rest of the code, the user can provide the knowledge of how to multiply or how to assemble the internal indices like color, spins, Lorentz indices, or whatever the tensor nature of your field is that you're dealing with, external to the stencil code. So we've separated the design into something that knows about the geometry of the stencil and something that knows about the physics of what it is that's being operated on with the stencil. And you'll note clever things like we can also use streaming stores in the output and so on to accelerate the application. So this actually, believe it or not, this is not as pretty as the C-shift based code, but this is the high performance code out the library. So it's not impossible to write. In other words, with that kind of stencil structure in the library, arbitrary dimensions, arbitrary data types, we can write reasonably high level code and get between maybe 18 and 30% of peak across a broad range of architectures here. So this, at least in the multi-core CPU domain, is giving us pretty good performance portability across these, and doing so in a way where we have threading, vectorization, and MPI all targeted under a single high-level data parallel interface. So you can see, in particular, the 960 gigaflops on Lake's Landing is pretty impressive. This is single precision figures, I should hasten to add. So if we compare to QDP++, this is now comparing the same line of code, the A equals B star C, to our new package and the C++ compilation of the QDP++ package. It also has SSE specialized versions, but not as yet, as I understand it, AVX and AVX2, on an AVX-based quad-core. We get, this is peak. This is the stream's memory bandwidth limit. We're doing better than that inside L2 cache and fall to that out of cache, and are getting 65% of peak within the L2, and in this region, about a 5.5 times speed up over the QDP++ package, which I think is quite an impressive result. We can compare now running the memory system benchmark inside grid, which plots the memory bandwidth delivered per thread, summed across threads, versus the footprint per thread as a function of the footprint per thread. And you can see that we get almost 2.5 terabytes a second out of a night's landing, falling to the stream's limit of about 400 gigabytes a second out of cache. This actually agrees with or slightly exceeds Intel's memory latency checker MLC program across the board. So I think it's doing as well as you can, and again, done with high-level code in the system. Now, the bad news. I can beat the compiler, right? So the bad news is that, so this plot shows a performance versus memory footprint on a combination of Knight's Landing and Broadwell. So the points that spike up and fall down as they fall out of cache are the results on a dual Broadwell. And you can see that this is 2 Broadwells versus 1 KNL. And you can see that KNL we're getting between 960, falling a bit to 700, and back up to 860 gigaflops in single precision across the board, with no appreciable fall off because it fits within the high bandwidth memory across the board. Whereas dual Broadwell will give us 800 and fall out of cache pretty rapidly. and end up being maybe 3 times slower than a single KNL, which is quite impressive. However, the bad news is, in order to do this, I got an extra factor of 2 by dropping from this fancy C++ inline intrinsics blown away class system and simply writing inline assembly in the end. Whereas with Broadwell, we can get away with sticking with C++ because the out of order is so much better in that chip. I've dropped inline intrinsics here, beaten the compiler by almost a factor of 2. I'm having to hand software prefetch to L2 and from L2 into L1, in addition to having the hardware prefetch enabled. I'm using an 82222 cache blocking in order to get the maximum reuse within an L2 tile that I can get. I had hoped for more, but I'm only getting a 1.7x reuse in the L2 tile because the tile capacity is so small. The single core instructions per cycle after all this effort is 1.7 out of a possible 2, which is not bad. Multi-core, the L1 hit rate is 99% out of obviously a possible 100 because I have prefetched into the L1 so aggressively in the code. So that's perfect software prefetching. And we're hitting 97% of the available read bandwidth out of the MCD RAM in the code once we're finished with it. So I would argue at this point the code is probably provably unimprovable. That said, I said that 2 months ago, and then found an extra 12.5% because I started using streaming stores in the kernel, which avoided the read, modify, write cycle on the written data. But now I think it's provably unimprovable. But I've been wrong in that in the past. Some tales from the trenches. Best performance is achieved with 1 thread per core in this due to my careful use of assembly. The reason for that is because having got the pipelining really good, I minimize stack traffic because I can allocate the registers by hand, so there's nothing living on the stack that can be evicted by the streaming data for this kernel. Right, that's why I'm using assembly actually, because to take control of the register allocation. And the result of that is that and the reason having done all that for 1 thread per core is then inter-thread L1 evictions are minimized because there's no other thread. The L1 will behave deterministically. So I have complete control over what it's doing. The hand allocation was important because I don't have stuff that was in the stack being needed and reread by the core being evicted by the data that I'm reading in an unpredictable way. I found it very important, as did the example from libxSMM, to use maximally complex instructions because there's only dual issue in the chip. So I was using this load and broadcast across a vector and multiply and add in a single instruction. So you do 4 things with 1 instruction, which was particularly useful. And that it was best to issue both software L1 and L2 prefetches in addition to the hardware prefetcher. This may be because the hardware prefetcher never crosses a memory page boundary, for example. I found it really great. There's a library that Andy Clean at Intel wrote called PMU Tools. I found using that and read performance monitor counters via RDPMC instructions really useful. For that, I needed root access to one of these DAP platform systems, but it made a big difference and led me to discover certain things and speed it up. Using these and some secret sauce that Larry Meadows at Intel gave me to read MCD RAM performance counters, which I believe are public and I can share with anyone if you drop me a mail, I was able to verify against theoretical the number of L1 writes per iteration of my loop, number of L2 reads per iteration of my loop. I can measure the reuse rate in the L2 as 1.7 directly from these counters, and the writes per iteration and so on. And you can see theory against what I measured against what I expected, and it's all spot on. And because of the small L2 tile capacity, I haven't been able to get the level of reuse I would like. I'm also not able to successfully get good performance by having L2s transfer direct to each other within the core. I haven't been able to figure out why, but maybe somebody at Intel can tell me, but we're having to maximally separate the tiles and work in disjoint data rather than trying to use transfers within the chip. Yep. The C++ for the kernel looks something like this. Inline assembly doesn't have to look completely ugly because you can use macros. So it looks almost the same code, in fact, in terms of so all the branch structures in C++ and only dense sequences of arithmetic is done in the inline assembly. And now finally, with the remaining 5 minutes, I'm going to have a little go at multi-node performance and just a few general digs, or far be it from me to say nothing controversial, right? So first thing I'm going to say is that traditional computer engineering accepts locality optimization at every level of the supercomputer except for interconnect. Why is that? We know that interconnect is the only region in supercomputing where a 4-bit bus costs us $1,000 without counting the switch ports on either end, right? The ports on either end. So surely it's an insane proposition to not go for locality in the network and have careful job placement to maximize locality. So I would argue that fully general networks is, full fat tree switches with full bisection bandwidth is not the price optimal point, because these bits are the most expensive bits in the computer. Okay, if you get it right, even on a torus machine which doesn't have full bisection bandwidth, we get perfect weak scaling all the way out to, in fact, 1.6 million cores. We regularly sustained over a petaflop in Myra, for example. So now that said, and with the bandwidth analysis that I introduced at the start, we can estimate the network bandwidth we require in a number of different systems by looking at the delivered performance single node and taking this 1/L factor. And we can see that for QCD, QCD is a particularly difficult problem because it's 4-dimensional, not 3-dimensional, that we can easily, on current nodes, hit, we want something like a 16 to the 4th local volume, 128 to the 4th global volume, so we hit 8 to the 4th, a good factor of 10,000 nodes that we can run on. We can easily hit 64, 128, oh my god, these 8 GPU systems, a terabyte a second network requirement, when the delivered is stuck down at 10, 20 gigabytes per second, typically for send plus receive added together, which is an absolute disaster. So you can see the delivered measured from Core A1, Theta, various Broadwell nodes from SGI. So here we have interesting commodity EDR, 23, 45 delivered compared to the 10 or so out of Core and Theta. Ouch. And then when we see these figures, we can see that Summit and Sierra are unlikely for our problem to scale beyond one node, which is not great. So here I think that the combination of dual omnipath on KNLF and omnipath 2 in KNH is really significant and important for QCD. I'm quite excited about these machines. These are results from the Theta workshop last week. It's maybe 10% slower than the corresponding Haswell node, but delivering as we expect for the Aries network. But it'd be really nice to see KNLF results with these dual rail omnipath with potentially 50 gigabytes a second peak bidirectional. So I've done a project with SGI in the remaining 2 minutes. I've done a small project with SGI where we've revisited yet another concept from the connection machine, which is the gray counter encoding of the hypercube, because the connection machine had only nearest neighbor shifts in its network. And the idea is that we can take an arbitrary torus, this is a 2-dimensional torus, embedded in an 8-dimensional hypercube in a way that the nearest neighbor is always the nearest neighbor. And the trick to this is something called gray counter encoding of your coordinates, because the gray counter only moves 1 bit at a time as you enumerate the integers, which means that you only hop by 1 link in this network. And when you map the torus onto the hypercube correctly, you can get perfect weak scaling across the board, including 45 gigabytes a second bidirectional, with no loss as you weak scale out in this halo exchange problem. So you can see here the performance delivered versus memory versus packet size, 45 gigabytes a second, which falls out of cache and drops on a Broadwell. And my hope is sincerely, and I wait to see the results from KNL with dual omnipath or indeed dual EDR, whether there is no drop out of cache because of the high bandwidth memory in KNL. So I really look forward to seeing how network evolves in KNL as we start integrating dual 100 gigabits ports on them. So this is a result that SGI ran for me very kindly on the Cheyenne machine, which is going to go into NCAR. This is on the floor at SGI. It's going to go into NCAR soon. Up to 2,048 nodes now with single rail EDR. You can see scaling perfectly in this halo exchange problem all the way out to 2,000 nodes. Perfect weak scaling. No drop off in bandwidth per node as you increase the system size, because we have mapped nearest neighbor as nearest neighbor. And you can see here the relative performance of this perfect gray counter encoded mapping on the hypercube compared to the naive MPI Cartesian communicator the MPI would give you. And you can see that on small systems, of course, the ratio is just 1, as you expect, because they all live in the same node. But as you scale out, you can gain up to a factor of 4 in the halo exchange performance if you get the mapping correct, which is a very nice result indeed. So in the remaining 0 seconds, I will summarize. We've implemented a whole bunch of stuff that's really interesting to QCD people. From your point of view, for most of you, this will mean lots of algorithms, lots of different discretizations, lots of functionality people want. We are worried about communications. The thing I'm going to look at next is reduced precisions communications in our Krylov solvers as a preconditioner so that we can, for the most of the matrix multiplies, shrink the comms footprint by a factor of maybe even 8 while still retaining full precision in the outer solve. And for the rest of the audience, I would emphasize that I could beat the compiler by maybe a factor of 2, only by a factor of 2. It's not so bad, but we can get within a factor of 2 of hand-coded assembly with pretty general C++ and this fantastic elaborate C++ template metaprogramming framework. So you can beat it, but not by much. That's it.
Yeah, I'll have one really quick one. So you mentioned performance portability a couple of times.
Yeah.
Focused on multi-core CPUs, or are you also interested in porting grid to other stuff?
Am I interested in?
Well, using grid on other architectures.
Of course we are. That's a longer-term challenge. There is this ECP round in the DOE, and we're interested in using Summit and Sierra, but it's not my primary focus, but it is a longer-term goal because we have, once we have this, I have a little prototype. We have this 180 line of code expression template engine. I've developed a small proof of concept that we can make this expression template engine offload to GPUs at compile time. Everyone else is doing just-in-time compilation, so we can do it at, this revived yet another ancient concept from computing, compile time compilation. You type compile and your code compiles. It's really nice. Most people should try it someday. Yeah.
I think we should thank our speaker.